Okay, so welcome back. The topic today are symmetries, and in contrast to last time where I didn't have much to add to what I've written in the lecture notes, here I would like to add a little bit, but let me start with the usual question, if there are questions. Something coming up already now? No. I want to add something, I want to add actually a general remark about symmetries, because very often I experience that some of you have the feeling symmetries is something which we invent. Whereas in reality physics, symmetries is something which we deduce. The symmetries are there. I mean, once a Lagrangian is given, the symmetries are there, we just have to find them. It's not that, that we invent something there. And I want to make this clear with an example concerning parity. Of course, the Lagrangians come from somewhere. It's not that nature gives us these Lagrangians. I mean, we have to construct them at some point. They are constructed typically such that some symmetries are satisfied because one first had gone through some phenomenological analysis. For example, found some reactions which do not happen. One has formulated some exclusion principles, and then at a later stage one has found, well, one can explain that exactly by having some symmetries. I mean, we will go through that very often in this course, where we will see specific reactions are forbidden and therefore things are stable, or at least are stable, say, with respect to the strong interaction or whatever interaction we are discussing. So of course, historically, when one sets up Lagrangians, one already has in mind one wants to satisfy specific symmetries, and one constructs them in that way. But it can appear that after having formulated a reasonable Lagrangian, and then analyzing this Lagrangian, it could happen that one finds additional symmetries, which one has not put in, which just come about because, well, this is the Lagrangian which describes the data, and it produces something else. For example, next time we will come to the Lagrangian of quantum electrodynamics, and if one basically applies only two principles, and that is, I mean, we'll come to that next time, by saying, well, all interactions between my electrons should happen via the photon fields. So I do not write down electron-electron interactions without involving photons. And I have, as we will see, a so-called gauge principle which tells me how the photons should couple to the electrons. And third thing, I put in that the photons are actually vector particles and not axial vector particles, or something which does not have a well-defined transformation under rotations, under parity. So if I put this in a sense, how the photons couple to electrons and that the electrons do not couple in another way to each other, by just putting that in, it turns out that the whole Lagrangian is parity invariant. And this is not so trivial. If one does the same thing for QCD, and we also will come to that, one could invent an additional term which breaks parity symmetry, which actually breaks parity and charge conjugation symmetry, and even the product of that. So it breaks everything, all discrete symmetries, parity, charge conjugation, and time reversal. one cannot construct such a term for QED. Actually, one can construct it, but it does not contribute to the equations of motion. It has no physical significance. So QED, just constructed basically from a gauge principle, shows an additional symmetry, which is parity symmetry, whereas QCD does not. There one has to, well, further limit the possible terms. So this is quite nice. Sometimes additional symmetries just come, just one finds them afterwards. In that sense, I mean, what I try to tell you is, of course, in the course of finding the right theory of some physical processes, I mean, one has to put in some symmetries, which first one has isolated from experiments. But once this is done, I mean, once I have a Lagrangian, then I can start out analyzing the symmetries of this Lagrangian, and maybe I find more than what I put in. In any case, once I have a Lagrangian, it is the Lagrangian which tells me about symmetries. I don't need to put anything in addition. So, to make this statement a little bit clearer, let me discuss parity. Okay, so in the lecture notes I have written down some theories. So let me start with the Yukawa theory. All this is about parity. So example 1. I have given a Yukawa Lagrangian. This is to honor Mr. Yukawa, who basically proposed that the interactions between protons and neutrons at long distances are given by a pion exchange. So he basically analyzed proton-proton scattering data, figured out it's best described if one assumes that a pion is exchanged there, just like photons are exchanged in electromagnetic interaction. And then some years later, this pion was really found as a particle and not just as an exchange force. So this was one of the cases where one basically predicted a particle, not from already seeing it, but seeing some reactions which point to an exchange of particles, and then one predicts that this is a real particle, which then also should be possible to create that. Okay. So let me start with the Lagrangian. Well, this is to honor Mr. Yukawa, but actually it is simpler than what he has written down, and it's also slightly different. So suppose I take scalar fields. This is the ordinary kinetic term for scalar fields. I add a mass term for the scalar fields, and I add a fermion, also with its kinetic term, its mass term, and now finally comes the interaction. This Lagrangian has a parity symmetry. So Ly is invariant. With respect to the following changes. So parity is that I do not change the time variable, but I basically flip my spatial coordinates at the origin, and I also perform modifications to the fields. So time does not change, spatial coordinates, I wrote them with an r, change to -r, and this I call r prime, and this are also called t prime, and the whole thing I call as a 4 component object x prime. And then my field at the old position changes into a new field at the new position, and of course I should relate it to the knowledge from the old fields. And I assume now that this is the case. The new field at the new position is the old field at the old position, and the fermions transform in a more complicated way. The new field at the new position is some phase which is actually irrelevant, and I multiply a gamma 0 with the old field at the old position. If you plug these modifications into the Lagrangian, actually I should say the action is invariant against that. So if I plug this here in and calculate the action, then this is invariant, and this is what I want. I have also given you another Lagrangian, and there I said, well, it also has a parity invariance. However, there the transformations look differently. So let me also write down this and then compare the two. So if I take now an L, because I've forgotten how I called that. I just call it, again to honor Mr. Yukawa, I call it Ly, but with a twiddle. So this is a new Lagrangian now. It looks very similar to the old one. It has, concerning ordinary Lorentz transformations, this is again a scalar. I do not distinguish the masses now. I mean, these are basically two interactions in two different universes, okay? I mean, I don't want to compare the two now, or combine the two. And I want to have here an I times T twiddle times phi times gamma 5 times psi. And the action as twiddle y is invariant with respect to the following. So I again do t to t, which I call t prime. I shift r to minus r, which is r prime. I shift. So now it's my point to be a little bit careful. Yeah. So then I shift phi of x to phi prime of x prime, which I now take as minus phi of x. So let me stress that this is actually the only difference here. And I change phi in exactly the same way as before, e to the I alpha gamma 0 psi of x. Okay, let me first start discussing this. So if one plugs these modifications into the Lagrangian, replaces everywhere the psi by psi prime of x prime, the phi by this here, the psi bar correspondingly, then it turns out the whole action which I get is the same as before. which means it is invariant. Okay, fine. Up to here nobody usually complains. Then I say, well, let's look at the new Lagrangian. If I do these changes here, this Lagrangian is invariant. And then usually some people start to complain and say, well, you put that in. You put in that you want to have a minus here. Why not taking these transformations? They do not work with this Lagrangian. So in that sense, isn't it me who has put that in, who has chosen these transformations such that it works? Well, actually not. And this is my statement again, the symmetries are in the Lagrangian. I don't need to put that in. The issue is, I'm completely free to choose any transformations I like. As complicated as I can imagine, and believe me, I can imagine very complicated transformations. I can explore every possibility. And probably, I mean, strictly speaking, I cannot explore every possibility because this would take my whole life. Because, of course, there are infinitely many choices of figuring out transformations. If I find transformations which change my Lagrangian, I have not ruined anything, but I also have not gained anything. So yes, it's true, these transformations here do not leave this guy here invariant. But this does not mean that there is not a symmetry. It just means out of my infinitely many possible transformations, I have chosen one which does not work. This does not tell me that there is no symmetry. It just tells me this transformation is useless. This is very different, these two things. Whereas if I choose this here, from my infinitely many possibilities of choosing transformations, if I choose this here, then this object is invariant. And if I find an invariance, I have found a symmetry. And from this I can deduce something. And one calls it parity symmetry because on the level of space and time it is related to this here. If it would require to make more complicated changes to my fields, and if then still I find a symmetry, I still would call this parity symmetry. Because it is related to a well-defined thing for space and time, and then for a corresponding change of the fields, whatever it takes to do that. So this can be really, in principle, arbitrarily complicated. So the message is, I explore many possibilities. For example now, this is my God-given action. Historically, of course, it's different again. I mean, I have at some point constructed that, but suppose someone gives to you, someone like me, gives to you this Lagrangian, then let's see if there is a symmetry there. Then one explores this here. Okay, we have not found a symmetry with these transformations. Nothing wrong with that, just means we were not clever enough to find a good transformation. Because this here is a good one. So if I come up with a transformation which in the end does not work, this does not mean that nothing works. It just means this one does not. If I find any transformation which gives me an invariance, I have isolated a symmetry. Again, I've isolated that. I have not put it in. I figured it out, that it contains something. And whenever I have a symmetry, typically problems become easier. This is more easy to see with continuous symmetries, but already parity, allows me to classify states. We will also come to that when we look at hadrons, that one uses parity to characterize them, to distinguish them from others. And if parity is conserved, a state which has a positive parity cannot suddenly change into a state with a negative parity, because then parity will not be conserved. Okay, so it's really to isolate that from a given Lagrangian and not something which is an invention. And of course, there are also cases where one cannot find a parity symmetry at all. For example, my last example was to couple such an interaction with a gamma 5 with that, but with the same scalar field. Then this interaction is just such that one cannot find a parity transformation. Well, maybe you can find one. At least I was not able to find one. This also includes, in principle, the possibility that our present-day understanding of particle physics, the standard model of particle physics, it could be that tomorrow someone comes up with a very, very clever additional transformation which leaves the standard model invariant, and maybe he can derive from that very nice features. Okay? Again, I mean, these transformations can be arbitrarily complicated. Maybe someone finds a new transformation which tells us something new, which we have not figured out yet. Completely possible. It's not that we have explored the range of all possible transformations. This is probably hard to do. There is, just maybe to stress again how complicated transformations can be. There is a transformation, there is a symmetry in some special systems of mechanics and quantum mechanics, which is rarely discussed, and this is the so-called Runge-Lenz vector. Have you ever heard about that? Maybe. Okay, let me start with classical mechanics. The fact that the Earth moves around the Sun in a plane, this is due to rotational invariance. That the force between the Earth and the Sun just depends on the distance and not on the direction. An immediate consequence of that is rotational invariance, and rotational invariance brings along a conservation law, angular momentum, and the angular momentum vector basically then must be a constant, and in that way it defines a plane perpendicular to this constant. This plane cannot change because the vector is constant, does not change its direction. And in this plane all the motion takes place. Okay, but that's not all about Earth. Earth has an additional property when it rotates around the Sun, and this is that the orbit is closed. It is on an ellipse and not on moving somewhere in the plane such that it never comes back to the point it started from. Actually, it's not completely true. It's not completely an ellipse because the other planets influence the motion and they distort that. But if the Earth was alone in the solar system, it would be a completely closed orbit. This is actually a second conservation law. That's the so-called Runge-Lenz vector. The Runge-Lenz vector points basically from the Sun to the point where the distance between Earth and Sun is biggest, or smallest, does not matter. But say biggest, this is a unique definition, smallest also would be a unique definition. And if the orbit is closed, obviously this vector always points in the same direction. Okay, the Earth goes around once, then it reaches the point of being furthest away from the Sun. If the orbit is closed, this is always at the same point. If the orbit is not closed, then this would change this point where it's furthest away. Okay, so this is actually a conservation law, and this conservation law is specific for 1 over r potentials. It would not work for a 1 over r square potential. 1 over r square is also rotational invariant. The motion would be in a plane, but it would not be a closed orbit. So this is very specific for a 1 over r potential. And by the way, this also has an impact on quantum mechanics. Quantum mechanics, the Earth-Sun system is basically like the hydrogen atom. The hydrogen atom also has a very specific feature, which is not only rotational invariance, and this is that the energy levels do not depend on L, on the angular momentum quantum number. Rotational invariance only tells it does not depend on the m quantum number. This is rotational invariance. But that the energy levels are also independent of L, not only of m, of the magnetic quantum number. This is again actually this Runge-Lenz vector. This is again this feature of the 1 over r potential, which has a bigger symmetry than rotational invariance. Why do I tell you all that? This is a case where it's actually straightforward to write down the conservation law. This Runge-Lenz vector, one can also formulate, by the way, in quantum mechanics. It's easy to write it down, I don't want to do that now, but it's easy to define it, easy to show from the equation of motion it is conserved. And it's also easy from the ellipse to show that it really points to the point where the distance is biggest between Earth and Sun. There it's easy to find the conserved quantity, but actually to find the symmetry of the interaction is very complicated. This is an extremely complicated transformation. One can write it down. Actually, I cannot because I never looked it up. But it is a symmetry which connects basically, well, of course, all three coordinates in a rather non-trivial way. Also, I mean, connecting that through that one rescales actually the energy levels and so on. It is a very, very complicated symmetry transformation which actually leads to a not so complicated conservation law. This should tell you, I mean, without writing that down now, this should tell you sometimes finding symmetry transformations can be rather complicated. Sometimes it's even easier to find the conserved current or the conserved quantity. So symmetry transformations can be complicated. Again, maybe one comes up with very complicated transformations which give us a new picture on some theories which we know since a long time. But it's always something which one deduces symmetries from Lagrangians and do not put them in. The message is just you can come up with arbitrary transformations. If they do not work, you have not lost anything, but you also have not learned anything. But if you find one particular one which leaves your system invariant, then you have found a symmetry. So it's not that I invented that. I explored several options and found one which works. Okay, yeah.
It's maybe a bit on the side, but it's Runge-Lenz. It's okay. It's conserved in like quantum mechanics in quantum field theory, but in this case with gravity, it's not in general relativity.
That's right. That's true.
This movement of Mercury around the sun.
That's right. I mean, this is a property of Newtonian mechanics that one has the 1 over r potential. That one has a strict 1 over r potential. I mean, also in general relativity, of course, you have rotational invariance. So the statement that the motion is in a plane is still true. But actually, there are modifications to the 1 over r potential, which, of course, become more severe the more curved the space-time is. And it is more curved if you are closer to a massive object. And therefore, the effect, indeed, of general relativity is that, so first of all, the potential between any planet and the sun is not exactly 1 over r, but has a modification. It has a 1 over... Actually, I don't know. Either it has a 1 over r square or 1 over r cube modification. So it has a modification, and it's biggest for planets which are closer to the sun, and therefore for Mercury one can really see that. And it was, I mean, historically one of the cornerstones of general relativity that one could explain quantitatively the perihelion motion of Mercury. Again, this is not the only effect. Actually, Mercury is influenced also by the other planets. which also lead to a shift of the perihel. But this one knew at that time, and one could actually calculate that. And it was just not enough to explain the motion of Mercury. So that time one knew already that modifications to the 1/r potential lead to a perihel motion, but one could not quantitatively understand what's going on with Mercury. And general relativity explained that, and this was one of the early successes. So this really gave a push to the theory that, well, as always, I mean, this is how physics should be. If you can explain something quantitatively, ideally quantitatively, which no one could explain before, well, probably you have something better than the present day theory. Okay, any further questions to that? So, why parity is important, I would like to postpone to when we characterize our hadronic states. More important are actually continuous symmetries as compared to these to this discrete symmetry here. And I have discussed, well, this intimate relation between continuous symmetries and the existence of a Noether current. And, well, maybe I can give one more example here. But, yeah, let me first ask you back again. Is there something which immediately comes to your mind now, what you would like to discuss concerning Noether currents? Okay. So the so basically, I mean, what I've given in the lecture notes was something rather abstract. So basically, I've postulated a transformation law without writing down a Lagrangian at all. So maybe as an example, let me just write down one simple Lagrangian which shows a symmetry, and then we can derive the Noether current which corresponds to that. So this is an example for a continuous symmetry. I don't want to make it too complicated. Let me check first what I actually did. So suppose so let me take one Lagrangian where I couple a lot of complex scalar fields in a specific way, in a universal way, to one other, well, real scalar field. Just for the sake of an example, what I have a little bit in mind is that this is very similar to the things we will discuss later on, where one couples to matter fields, well, forces like the photon exchange or gluons or W bosons for the weak interaction. Here I want to keep it much simpler, just use scalars. In a sense, use scalars for the exchange forces and use scalars for the matter particles, but couple different scalars to each other. So I start out with complex fields. So there I always need combinations d mu psi dagger, d mu psi, and I have added here an index which can run from 1 to capital N. So I want to have not only one complex scalar field, but n many. Okay, so this is, you might compare that to the situation of quarks in the standard model, where one does not have one type of quark, but actually 6 of them. One has the up quarks, the down quarks, the charm, strange, and so on. Actually, I make it rather simple and ignore mass differences, so I really want to make it extremely simple. So I assign to each of these complex scalars now the same mass. Yeah. And I want to add one more particle. So this now should be the correspondence to matter fields, and now I introduce one force field. Of course, this is also kind of matter, but I mean, just that you know what I'm after. And this field I call, for example, chi, and this should be an Hermitian scalar with another mass m squared, chi square, and finally I should write down an interaction. And basically what I want is that this chi does not distinguish between the different phi fields. So then I want an interaction, for example, actually it does not matter what we write down now. So minus g chi phi a dagger phi a. And in here, the sum over A is implicit, which means this here is d mu phi dagger 1, d mu phi 1 plus d mu phi dagger 2, d mu phi 2, and so on. Okay, then okay, now actually L is symmetric basically if I mix up my different phi fields. So I have n, capital N, many phi fields here. If I replace, say, phi 1 by a linear combination of phi 1 and phi 2, or a linear combination of phi 1, phi 2, and phi 3, and so on, and if I do this in a well-defined way for all the phi's, this Lagrangian does not change. So L is actually invariant with respect to the following changes. If I change phi A by, now I introduce a matrix by U A B phi B, again here the sum over B is implicit. And then this implies that the daggered fields should transform like I see U, of course, dagger C A, and I want to I do not want to change the chi. The chi I completely leave invariant. For this U, so this here is an n times n matrix now, and this U, if this U is a unitary matrix, which means that U times U dagger is unity. Or let me write down this in components, that U A B U dagger B C is delta AC.
The transformations of phi dagger, you should be a dagger of the phi C.
Oh, that's right. Thank you. So I wrote this here not as a new line, because this here follows from this property here. I just take, as Olaf said, I just take here the complex conjugate. I don't want to invent a new rule here. And then, of course, it should be a dagger. Okay, first of all, let me show that this is indeed true. So, first of all, let's look at these derivatives here. So this is supposed to be now a proof first. So, one more time, if you see double indices here, this means summation, and the summation index runs from 1 to n for these n different complex valued fields. I basically plug this in now. I want a modification of my fields of the phi A dagger. This is supposed to transform in that way. So this is a d mu phi C dagger U C A. And the phi A itself transforms according to this here. U A B phi B. Now these UAs, I have not specified any spatial dependence here. Actually, they are supposed to be constant in space and time. Let me add this here. So this is with constant entries. So this is an n times n matrix with just some constant entries, however chosen such that U times U dagger is unity. Then this derivative here does not act on the U's, on the different components of U, because they are space-time independent, they are constant. So I can take this, well, just acting on the phi. So this is a d mu phi C dagger, U C A, U, I missed the dagger again, U dagger, U A B, d mu phi B, and now comes my property. All this works only if U is a unitary matrix, because then this here is, well, the CB component of the unity matrix, which is delta CB. So this is d mu phi dagger C delta CB d mu phi B. And here I assume a summation over C and B, because both indices appear twice. Well, but this summation only gives a result if B and C is the same. So this breaks down to one sum, which is d mu phi phi C, which, except that I call my summation index here C, and in the beginning I call it A, is the same as before. Okay, good. So the kinetic term does not change. The phi A dagger phi A, which appears here in the mass term, and which appears here in the interaction term, and the rest actually does not change at all. Well, this here is, of course, the same as before, because, well, with the same logic as here, but just without derivatives. So this is phi c dagger u dagger ca u a b phi b, and this is phi dagger c phi c again. So this means that L just changes to L, which is, well, which is what invariance means. So I have to use this property that U is unitary, but that's all. In principle, well, we could now decompose this U here. Actually, there are a lot of matrices which I can construct which are unitary, and well, mathematically this is now called group theory. One can analyze how one can write down all possible such unitary matrices. This was something which will actually show up later again in the in these lectures, because we will need that for QCD, where basically counting this here is, well, enumerating the different colors of the quarks. This I don't want to do now in full glory. But at least I wanted to show you, in one example, well, how symmetries, mixing up different components, how that can look like. Now I would suggest we make a break, and afterwards we will look at one even simpler case where I want to explicitly construct the Noether current and convince you that, well, there are actually two ways of seeing that the Noether current is conserved. One way looking at symmetry transformations, and the only way basically by a brute force calculation. So this I would suggest we do after the break. And I'll make a break till... Okay, so let's continue. Questions so far? So let me even more simplify that and, well, derive the Noether current, and also show you in a direct way that it's really conserved. And this touches also something which, well, creates some misunderstanding. The simplest case, what is the simplest case I can imagine here? What do you think? Well, if capital N is 1, exactly. If capital N is 1, then the Lagrangian is simply, let me copy it again, is du phi dagger. I drop the index now because there is only one complex field. This was small m. And there is this, I keep of course the field which causes an interaction. Minus g times chi times phi dagger phi. unitary matrices for the case n equal 1 are 1 times 1 matrices. So these are just numbers. And, well, how do they look like?
Yeah, modulus 1, so e to the I.
Exactly. So these are just phases. So the symmetry transformations are that my phi is modified by a phase. The phi dagger is then modified by the opposite phase. And the chi is unchanged. Okay? And this is a symmetry for any value of real alpha. Okay, I do not want to take here complex alpha, otherwise this would not be a phase. I mean, then, by going from here to here, I have assumed one of your remark applies again. Going from here to here, I have assumed that alpha is real, otherwise this would not change to minus I alpha. And then this would not drop out. This is what one calls a continuous symmetry, that I can have arbitrary values of alpha, which are continuously connected to each other, and well, make these transformations and nothing changes concerning the action. Actually here nothing changes concerning the Lagrangian, then nothing changes concerning the action. In principle it's enough if the action does not change. Good. For the conserved Noether current, what one considers are infinitesimally small transformations, which is a sub-part of all possible transformations. In this case, I can actually build any phase shift here out of a succession of very, very small phase shifts. Okay, I can take a very, very small phase shift and add another one of these and another one and another one, and I end up with whatever phase shift I want to have. Therefore, since every phase shift is just a succession of infinitesimally small phase shifts, the whole information is actually contained already in looking at infinitesimally small phase shifts. There is not more information contained in the whole symmetry group here. If I look at then these small transformations is in a sense infinitesimally small, and I keep terms, well, as always in mathematics when one looks at infinitesimally small quantities, I consider the terms linear in this small quantity, but I drop quadratic and higher order ones. In this sense, then the phi changes to, if alpha is small, I can for any alpha I can tele-expand that, but if it's small I can stick to the linear terms. This phi then changes roughly to 1 plus I times alpha phi, which is phi plus I alpha phi. So this here I would like to call the change due to the symmetry transformations. This is a delta phi. The phi dagger correspondingly changes to phi dagger minus I alpha phi dagger, and again, this whole thing I would like to call delta phi dagger. And finally, the chi changes to chi, which means the delta chi is 0. So that's pretty trivial. However, I would like to keep this. And now I apply my machinery how to construct the Noether current. Well, from the lecture notes, I obtain the Noether current by well, general formula for the Noether current was that I look at derivatives of my Lagrangian with respect to the fields. And then I take, I take basically this parameter which characterizes the change of the fields times the field itself. Now comes the important remark. There is not a Noether current per field. If I have one symmetry transformation, one type, there is one Noether current. There is a sum here over all possible fields. And all possible fields in my case are three different ones. The phi dagger, and the chi. So this might now be a little bit of confusing notation. These phi a's here are not so closely connected to these guys. These are completely general fields. They basically enumerate all types of fields which I have in my Lagrangian. So here the phi a is one of the guys from phi dagger, chi. And I have to sum over all fields here. So let me write this down in detail. So this is important. There is not a conserved current, a Noether current for my field phi, and a separate one for my field phi dagger, and a third one for my chi. There is one. Well, per possible symmetry, per possible infinitesimal symmetry transformation. And the T and the TAB we write down in a moment. No, we write it down now. So the TAB, this is my change basically of my field phi a, one of these guys, times whatever multiplies my field in the change of fields. So the TAB is, so let's see, how does the phi change? Well, the phi changes according to this rule here. This alpha is just a parameter. This is infinitesimally small but arbitrary. This I have scaled out already in this formula. You find the alpha also in the lecture notes. The TAB for this here is Well, I have the alpha, which is not included in the TAB. I have the phi itself. This whole thing was the change. The only thing which remains here is I for if the phi A is the phi. If the phi A is the phi dagger, what I have in here as a change is minus I. And I have, finally, if I have the chi here, well, there is no change, so this is 0 if the phi A is chi. And there are actually no mixtures between phi and phi dagger and chi, so the transformation of the phi solely contains the phi. It does not contain a phi dagger or a chi, and also true for the other for the other two. So in a sense I can say this also concerns here the phi b, and 0 otherwise. Then let's write down the conserved current. So this is dl d nu phi times the change in phi. Well, the change in phi was this here, so this is times I times phi plus, because of these double indices here, a sum is implied. So I have to add up this here with the same object, but with a phi dagger. And then I need the corresponding TAB, which is minus I times phi dagger. And for completeness, let me also add here the dl d nu chi. Well, times the modification of chi with respect to the symmetry, but this is 0. The chi does not change, so this is times 0. Okay, questions here? And now we just have to read it off from the Lagrangian. So in the Lagrangian there are derivatives acting on phi. Okay, which is up here. And if I take a derivative with respect to that, basically with respect to a d nu, I pick up the term where mu is nu. And what I get is, of course, this coefficient here. And if I do that properly with up-down indices, if you want me, I can do this in detail, but then you have to tell me, otherwise I assume that you know how to do that. The result of this here is a d nu phi dagger times I phi. A d nu phi dagger is also here in the first line, and by the way, there are no other derivatives acting on phi in the other terms. So there is a plus. D nu phi dagger multiplies here the d mu, or actually d nu phi. So this is a d nu phi times minus I times phi dagger. And this here I don't need to evaluate because it's anyway multiplied by 0. So the result of that is that this is I times d nu phi dagger phi minus d nu phi dagger. If you look at this expression carefully, actually you find that this is Hermitian. Actually, there is some arbitrariness in writing down a conserved current. So there could be cases where in this line of reasoning you could find a current which is not Hermitian. Could happen. Could happen that in the end you derive a current which is purely imaginary instead of purely real. It also could have happened that you derive a current which deviates from what I have here by a factor of 1 half. By a factor of 1 half, or by a factor of -1, or by a factor of 10. This does not mean that what you have derived is wrong. If a quantity is conserved, then also 10 times this quantity is conserved. Then also minus times this quantity is conserved. Actually, then also I times this quantity is conserved. So if one ends up with a current which is purely imaginary instead of purely real, you are free to multiply it by I. Then it's purely real. Why should it be purely real? Well, in the end you are after a conserved quantity which corresponds to an observable, ideally. Observables should be Hermitian, and not I times Hermitian. So no matter what you do, in the end, you have the freedom to multiply it by a number. And well, this freedom one uses to to write down something which is intuitive and which is Hermitian, where at least the charge, the spatial integral over the zeroth component of this guy here, well, this is Hermitian. In this case, this is true, I mean, from the construction. If one takes the complex conjugate of this here, one ends up with something where the derivative acts on the phi and not on the phi dagger. And this is exactly what one has here, and because of this I, the whole thing is actually Hermitian. Because there is a sign change here which is compensated by the sign change of the I if I take the adjoint of that. Well, let's check whether it's really true that this is conserved. Actually, we do now something which we have already used in the derivation of the Noether current, so in that way we cannot go wrong. But sometimes it's reassuring to see that it really works. So finally, we want to check that d nu J nu is 0. Okay, this is the conservation law. And we want to check that from the equations of motion. Well, let's do that. So first of all, how do the equations of motion look like? Now the equations of motion is something which I can write down separately for every field. This is different from my Noether current, which does not exist per field, but I have to sum up all contributions from all fields from their changes. Whereas of course the equations of motion must apply to every field separately, because I want per field to know how it behaves in time. Okay, equations of motion, they always derive from from the Lagrange equations of motion. So this is d mu dl d mu phi minus as dl d mu minus dl d phi is 0, and if I do that with the Lagrangian, which we have up there, I get my dl d mu phi. This produces the d mu phi dagger. There are no other terms which depend on this d mu phi, and I can create something from taking the derivative of L with respect to phi. And there are two terms up there. There is the m squared term, which comes with a minus, phi dagger, and there is this term with the interactions, minus g times chi times phi dagger. So if I write this here, rewrite this a little bit, this is d mu phi, and let me take out this overall phi dagger here, plus m squared plus g chi times phi dagger. And correspondingly, I can derive the equation of motion for phi. This is the equation of motion for phi dagger, but I can also do that by taking the adjoint of what I have already derived here. So this here is supposed to be 0. That's the equation of motion. And the corresponding one is that d mu phi. I just take the complex conjugate of that is plus m squared plus g chi times phi is 0. Now let's look at this here. Before I proceed, let me tell you, of course there is a third equation of motion for the chi, but the chi does not show up in my definition of the Noether current, and therefore I don't write down the equation of motion now, because anyway I will not need it. Okay, so d nu j nu. This is d nu of I times, here it is, d nu phi dagger phi minus d nu phi dagger. And okay, so I now have a couple of terms. Product rule. So this is I times d nu phi dagger. I distribute some brackets here that it's clear, at least now, where the derivatives are supposed to act on. I could do this here as well. Maybe that's more clear. So this derivative can act here or can act here. This is a d nu phi dagger d nu phi. Then I have one more term minus d nu phi times phi dagger, and finally the d nu can act here, which is minus d nu phi dagger. This term here, with one index up, one down, is the same as this, because I can always move one up, one down without changing anything. So this here together with that, because of the minus, is 0, and for the rest I can actually use the equation of motion. Two derivatives acting on phi dagger. This is exactly what shows up here. I've just, used a different label for my derivatives. Okay, this plus this here is 0, which means this alone is minus that expression here. So this is minus m squared plus g times chi times phi dagger times phi. So the bracket is this here times phi. This I've already got rid of. This here is minus d nu phi. Double derivative on phi is exactly what I have here. And this with this combination here is 0, so this here alone is minus that. Minus m squared plus g times chi times, where are we now? Phi times phi dagger. And
I think there are two minus. There should be only one minus. Where is it? Minus, minus.
Okay, so this minus here translates to that.
Yes.
Okay,
Ah, okay. And
So
then
this is
there
this.
further from the equation of-
and this minus comes from the equation of motion
yes.
here, because I have to bring this to the other side. And then there is one bracket still open, which is this here. And the whole thing multiplies the I. And now what you're supposed to see is that I have phi dagger phi combinations here, and in total I have a minus in front of this combination, and here in total I have a plus, which is I times 0, so this is 0. So also from the explicit equations of motions I found that this current here is conserved. And this brings me back iterating what I already said about 1 hour ago. So suppose from using equations of motion you have found a conserved current. This does not mean that you, well, this means that probably you have found a symmetry, but it does not mean that you have found the symmetry transformations. Of course, we have derived it now in two ways, in a sense. I mean, we have derived the current from knowing the symmetry transformations. This is what Mrs. Noether has taught us how to do that. But in principle, it's one can also imagine that when just by a good guess one has found such a conserved current. Think back on my Runge-Lenz vector. Then from equation of motion one could find that this is 0, okay, one has found a conserved current. Then concluding backwards how the symmetry transformations look like is not an easy task. The other way around is what Mrs. Noether has told us. If you have the symmetry transformations, it's straightforward to derive the conserved, in this case the conserved current, or in mechanics the conserved quantity, in the sense the conserved charge, the corresponding charge. But the way back is complicated. Okay, then it's time to stop here. We meet next time on Thursday, and then we discuss quantum electrodynamics as the first, well, part of the standard one. Then we are really there. We talk about interactions which, well, are real, which describe a part of our world. Okay, then see you on Thursday.
I have a question about this energy momentum tensor. Yeah, because
Or should we do that next time?
yeah, maybe.
Okay.
But it
Yeah.
was just I tried to check for Lagrangian with the fields and got so then I got something that should be like energy density or momentum density. It's like time derivative times spatial derivative of the field. And is there a way to see that, okay, this is the momentum?
You want to see whether you whether one can see that this is the right
yeah, or like, is this momentum of the field?
yes, you can do that by you know how what the total momentum should be when it acts on fields, because the momentum operator is connected to translations in space. So acting with a momentum operator on a field should in a very particular way change the coordinate of that field you're acting on.
This momentum generates translation.
Yes. So basically, yeah, we'll think about it next time that I bring this up again, but now I explain it to you. So, one wants that, so all what I write down is now true up to science. If I have say a momentum operator in the z direction, okay?
Okay.
So let me call this pi z. And if I multiply this by whatever, by a number, which is supposed to be a distance, and now this acts on something which, I mix up a lot of probably 4 vectors and not, but it doesn't matter. So if I do the following thing, I change. And in that way, I change the coordinate of my field.
Okay.
I mean, this is what you might recognize that from quantum mechanics, where one does that with the Hamiltonian and the time coordinate. But I can do this in space and time if I want. And I want that this here is basically phi of x plus and then z, well, basically times the unit vector in z direction. And actually I don't know the sign here, so it can be this or that. But this is a matter of, well, this here is not a matter of convention. Okay, either it's this or the other one. Now suppose I look at small values of z. Then actually this here, so I now expand in powers of z. So the left hand side is 1 plus I times pi z times z times phi of x times 1 minus I pi of z. The right hand side, if I expand in small powers of z, I can do a Taylor expansion here. So this is phi of x, again I don't know the sign here, plus or minus the deviation from my original point, so this is z, and then I would multiply this unit vector by the corresponding derivative of phi at the point x, which basically gives me the z derivative. So this is the phi dz at x. Now by comparing the left and right hand side in linear order in z, this tells me that I times pi Z. So here I have a pi Z phi, and here I have phi pi, so this is something to do with the commutator. Keep the X here. And on this side here, this is a plus minus, because I mean, it is definite, but I just don't know it by heart. And this is the T phi. Z. So why have I written that down? Because you could test now, when you have derived an expression for this, you could plug it here in the left-hand side and use the elementary commutation relations. You know the commutation relations for...
Condensation.
Yes, the quantization conditions. And you could plug that in and go through that and do some this usual algebra with the commutators, and either you find this or not. If you don't find it, and your initial, say, guess or derivation of the momentum operator was wrong.
Okay.
This here is the momentum operator. It's not the momentum density. So this here is really whatever you have derived. Now let me recall that. So this pi z is a T3x T 0, 3. I mean this, the T mu nu was the right? Yes, I think so. The T mu nu is the stress tensor density. And by integrating, you find this here.
Ah, okay.
There you go.